Welcome to the Deep Dive, the show where we take your sources, articles, research papers, field notes, and turn them into pure actionable knowledge. And today we are on a journey, a deep geological and societal journey across almost 180 years of Icelandic history.
We are. We're connecting a foundational 19th century scientific expedition with a really fierce modern debate about preservation, safety, and public access on one of the most restless pieces of crust in the world.
That's right. We've got sources from historical preprints on Robert Bunsen, and yes, that's the inventor of the Bunsen burner, who is also, it turns out, a pioneer geochemist, all the way to cutting-edge geophysical studies looking at the Reykjanes Peninsula and
Right.
legal research on Iceland's public access laws.
And this whole deep dive really pivots around one area, the Seltún geothermal field. It's a perfect case study, really, of this collision between pure science and modern mass tourism.
So we're asking two big questions. First, how did a scientist famous for a stable, controlled lab tool unlock the massive, chaotic chemical secrets of active volcanoes? And second, how do his discoveries from the 1840s still define the landscape that 2 million tourists now risk damaging every single year? Okay, let's get into it.
So the whole reason Bunsen even went to Iceland was because of a geological spectacle. In September 1845, Mount Hekla started a massive eruption that went on well into 1846. This was a huge event.
And Hekla, you have to remember, this wasn't just another mountain in medieval Europe. It had this whole folklore around it. It was seen as the gateway to hell, right?
Absolutely. Vomiting incandescent rocks with this terrible noise. It was culturally terrifying. But King Christian VIII of Denmark and Iceland, he saw an opportunity.
Not just a disaster.
Right. He invited Robert Bunsen to lead a major geochemical investigation to figure out what Hekla was actually made of, what it was venting. For a chemist back then, that was like getting an invitation to go to the moon. You just had to accept.
And it was a serious commitment. I mean, he didn't travel light. He brought geologist Sartorius von Waltershausen, physiologist Carl Bergman, and was later joined by the French mineralogist GlaciGo.
And their equipment was absolutely critical. The key tool was Bunsen's own invention, the eudiometer. It's this elaborate piece of glassware for analyzing gases. It let him, for the first time really, accurately figure out the composition of volcanic gas mixtures right there in the field.
Which meant the field work must have been grueling. This wasn't some scenic stop on the Golden Circle. Their trips from Reykjavik covered, up to 300 miles of just rugged landscape?
Oh, for sure. Think about the logistics. The sources say they needed at least 2 riding horses per person.
Per person.
Yeah, just to carry the gear and provisions. So if you're bringing 2 horses just to haul your scientific equipment across lava fields, you are seriously committed. He was probably prioritizing those delicate glass eudiometers over like a good night's sleep.
That intensity really speaks to his whole identity, which the sources call an ardent experimentalist.
That's what makes him so unique. He was, and I quote, vigorously opposed to hypotheses of any kind, a strict inductivist. He believed you had to collect a mountain of facts first, and only then could you maybe start to guess at a rule.
But wasn't that kind of a massive scientific blind spot for him? If he rejected hypotheses, didn't he miss the bigger picture that was emerging in chemistry at the time?
That's a great point. And yes, his dedication to just the facts was so absolute that he ended up dismissing these huge foundational theories of chemistry, like the ideas about molecular structure from giants like Dumas and Kekulé. He just thought they were too speculative.
So for him, the gas composition he measured was the only truth. Structure was just an idea.
Exactly, an unproven idea.
And yet, that ruthless focus on facts led him to huge breakthroughs in Iceland. Let's start with the rocks. His chemical analysis gave us a whole classification system.
It did. Bunsen, along with his colleagues, basically defined the Earth's crust based on one thing, silica content. He split igneous rocks into 2 main types.
Okay, so he called them trachytic and pyroxenic. Are those names we still use?
The names are updated, but the idea is foundational. His silica-rich type, the trachytic, we now call felsic. So think of rhyolite, those pink and red rocks at places like Arnarfell. They have incredibly high silica, maybe around 76%.
And the other type? The one with less silica.
That's his pyroxenic type, which today we call mafic. Mafic rocks are high in iron and magnesium, low in silica, maybe 47%. The classic example is basalt, which he studied all around Hekla. This 2-part system unlocked how magmas are built and how they differentiate.
It's amazing. And he didn't just stop with solid rock, he figured out the geysers too. The Great Geyser was surrounded by these wild theories at the time.
Oh, the theories were almost comical. People thought they were connected to the sea or that the eruption was caused by, sudden bursts of heat from somewhere else. Bunsen just threw all of that out.
So how did he solve it with just observation?
He took temperature readings at different depths, and he realized the whole thing works like a natural but inverted pressure cooker. Because of the pressure from the column of water in the tube, the water at the bottom has a much, much higher boiling point than the water at the top.
So it can get way past 100 degrees Celsius and still not boil.
Exactly. Then, when the water moves just a little bit, that superheated water in the middle suddenly hits its boiling point for that pressure and flash boils into steam. That steam creates this massive explosive bubble that just shoves the entire column of water up into the air. It was a beautiful, elegant piece of field physics.
And that preference for facts even caused fights with his own team. I'm thinking of his disagreement with von Waltershausen over how sal ammoniac or ammonium chloride forms.
Oh, yes. A perfect example. Von Waltershausen had this theory about deep, mysterious chemical processes. Bunsen just vehemently disagreed. He insisted it had an organic origin.
An organic origin, so from plants and things.
Right. He believed it came from vegetation or sedimentary rock, like old peat beds. They got cooked by the intense heat of the lava flow.
So the mineral was literally forming from the lava, cooking the landscape.
Precisely. And he proved it. He used this elaborate apparatus to analyze the gases from pyrolysis, and he showed that the ammonium chloride was just a result of organic matter being chemically broken down by heat. It just reinforced his entire philosophy. Don't hypothesize about deep magic when you can just look at what's burning right in front of you.
That scientific method leads us right to a specific spot he studied, the Seltún geothermal area. It's a place where science, industry, and danger all meet.
It really is. For centuries, before tourists showed up, it was an industrial hotspot. Seltún was one of Iceland's two main centers for sulfur mining, right up until the 1880s.
And sulfur was a killer commodity back then, wasn't it?
Absolutely essential. It was a critical ingredient in gunpowder, but it was also used medicinally for treating skin diseases like psoriasis. So whoever controlled the sulfur supply had a real strategic advantage.
And that control wasn't in Icelandic hands. It was a foreign monopoly.
For centuries. It started with Norwegian kings, went to the Hanseatic League, and then the Danish crown established a total monopoly in 1561. So you had Icelanders doing this brutal work to extract a resource that was being shipped away to fund foreign powers.
And the work itself. Digging in a high-temperature geothermal field sounds awful.
It was grueling. The sulfur deposits were sandwiched between layers of hard basaltic lava. Workers had to use hammers and picks to manually break up the rock, all in an environment filled with noxious gases and boiling mud. It was just industrial work layered on top of natural danger.
So Bunsen shows up at this historically important industrial dangerous site. How did he connect that to his own research?
Well, Seltún has these intensely acidic hot springs and fumaroles. Those are vents releasing steam and gas. Bunsen used these to figure out the natural formation of sulfuric acid.
Sulfuric acid, that's H2SO4, the really corrosive stuff. How is it forming there?
The vents release hydrogen sulfide, H2S. That's the rotten egg smell. Bunsen realized that when this gas rose up, it combined with oxygen and water in the air to create sulfuric acid, H2SO4, right there on the surface. That discovery was critical for understanding the whole system of hydrothermal weathering.
And that system is still hyperactive today. Seltún is this incredible multicolored landscape, yellow, red, orange, all because of that sulfur. It sits right on the mid-Atlantic ridge where North America and Eurasia are visibly pulling apart.
It is the definition of restless Earth. And now we have these incredible tools to look deep underneath. We use something called magnetotelluric, or MT, resistivity data, to see the internal structure.
Okay, hold on. What is MT resistivity data? What are you actually measuring?
It's a complex technique, but the idea is simple. We're measuring how easily the ground conducts electricity. Hot water makes rock more conductive, so low resistivity tells us where the hot fluids are. We can basically build a 3D map of the geothermal plumbing system miles down.
And what does that map of Krusevik show us?
It shows us a signature common to these systems. There's a shallow, low resistivity cap of altered minerals, and beneath that, there's a much hotter, deeper resistive core.
And why do those layers matter to someone walking on the surface?
That cap, that low resistivity cap, it acts as a seal. It's made of clay minerals that essentially plug the system, trapping immense heat and fluid pressure underneath. It's a natural pressure cooker, and that sealed system is what causes the violence when things go wrong.
And that instability isn't just theoretical. The sources document some really violent steam explosions.
Oh, the area is extremely unstable. On October 25, 1999, an old geothermal borehole had a violent steam explosion. It threw mud and rocks up to 700 meters away, completely destroyed a research shed. Another one happened in 2019. It shows the danger when that deep pressure builds up.
And the deeper data suggests the system is actually recharging.
That is the most concerning part. Recent measurements show a deep conductive body, a hot anomaly, that lines up with ground inflation at 4 to 5 kilometers depth. Something is pushing up from below. It suggests a deep magma chamber is rising or releasing huge amounts of gas. The danger is not historical, it's a current geological fact.
Which brings us to visitor safety. For the millions of people visiting this landscape, what are the absolute key takeaways about the gases?
You have to be hyper-aware of the invisible hazards. First, odorless carbon dioxide, CO2. It's denser than air, so it sinks and pools in low spots. If you slip off a path into a ditch, you could walk into a pocket with no oxygen.
A silent killer.
Yes. Second are the irritants, sulfur dioxide, SO2, and hydrogen sulfide, H2S. They cause headaches, nausea, irritation. So the advice is simple. Sturdy shoes, stick rigidly to the marked paths, and critically, check the wind forecast. Always stay upwind of the steam vents. Your safety depends on knowing which way the wind is blowing.
So we have this spectacular, scientifically vital, and dangerous landscape now being visited by millions. And this tourism boom has put catastrophic pressure on one of Iceland's most cherished legal traditions, allmanaréttur.
The public right of access. It's a cornerstone of Nordic law, the idea that nature is a shared resource. Basically, it gives the public the right to walk or use non-motorized vehicles across private land.
So how should someone from outside the Nordic countries think about this? Is it like a right-of-way?
It's more than that. It comes with a duty not to spoil nature. Landowners can't just fence off their land, but they have to provide a gate if it's needed for, say, agriculture. The problem is the law is designed for hikers and farmers, not busloads of tourists.
And when millions show up, that balance just shatters. The sources point to four main conflicts.
The first is preservation. Arctic soils are incredibly fragile. 1 million pairs of feet wandering off a path cause degradation that can take centuries to heal. The second is use and change of landscape. You need infrastructure paths, fences, bathrooms, but that infrastructure itself can be seen as spoiling the nature everyone came to see.
And then you get to the money and the paperwork.
Right. The third challenge is economic interests. Tour companies make huge profits using private land for free. The landowners are left with all the risk, the liability, and the cleanup costs. And the fourth, which people forget, is privacy for the landowners who live there.
It sounds like a guaranteed funding nightmare. If access is free, who pays for the infrastructure?
Landowners are often forced to use service fees, like for parking, as their only option. And that creates a huge controversy about the tradition of free access.
We saw that happen at the Geldingadalur eruption site.
Exactly. They had to bring in a 1,000 ISK parking fee to manage the chaos. But the real nightmare is when land ownership is shared. At a place called Veron, a service fee was introduced, but the Supreme Court ruled it illegal in 2016 because they didn't have consent from all 6 landowners.
So a single person, one minority shareholder, can veto a crucial safety or funding measure needed for millions of visitors.
That's the mess they're in. Landowners can't get permits for infrastructure, and they need 100% agreement from all co-owners. The legal system just hasn't caught up with the reality of mass tourism in a geologically unstable place. So when we synthesize all this, the contrast is it's stark. Bunsen's 19th century journey was this pure pursuit of knowledge. He was just trying to figure out the fundamental physical and chemical rules of Iceland's geology.
And today, we're struggling with the societal and legal rules needed to preserve that same geology. We've gone from calculating the silica in basalt to trying to calculate the consensus needed for a parking fee. The stakes are so much higher now because of the sheer number of people.
And the science itself confirms we need to be humble. The modern resistivity models show us the danger is not static. Managing a geothermal field means constant vigilance against these deep processes, whether it's a rising magma body or those shallow seals that can just pop under pressure at any moment.
You know, Bunsen was famous for his ardent experimentalism, for favoring collected facts over hypotheses. Given the extreme fragility of Iceland's landscape and these tensions around allmanaréttur, what core agreed-upon facts about capacity, liability, environmental cost, what facts do landowners, tourists, and the government need to agree on first before they even start to form a hypothesis about how to manage or monetize this shared, stunningly volatile natural resource? That question feels like a moral and geological eruption just waiting to happen.